Hello friends, today we are going to discuss one of the important theme in systems physiology, nerve impulse conduction, or simply called action potential mechanism. Nerve impulse conduction, simply action potential generation. When nerve fibers get stimulated, maybe because of external or internal stimuli, it leads to the generation and conduction of a nerve impulse, simply called action potential, that travels along the nerve fiber, which leads to generation of neurotransmitters. That means a momentary change in the membrane potential of a neuron is action potential or nerve impulse, which is an essential part or crux point for cell-to-cell communication. Okay, before we go into the topic, that means how the nerve impulse conduction mechanism done, we have to understand the environment, what we call neural environment present in a nerve fibers and its basic issues like gated channels, that means leakage, voltage gated channels and others, so that we can come to know how this mechanism proceeds. Okay, first I told an important word, membrane potential. Membrane potential. Okay. Just imagine this is a neuron, a basic structure, elaborating the same. Used to focus on this point. This is axolemma, this is axoplasm, this is ECF or outside environment. Say, okay. The thing is, membrane potential. Membrane is with respect to axolemma. Potential, what exactly the potential? Here, there is an unequal distribution of ions across the neurological membrane, that means across the axolemma, simply the nerve membrane, the neuron membrane. That means negative inside and positive outside. That means more negative inside, simply called membrane potential. And it leads to establishment of polarity. Certain important words and concepts we have to understand at the moment. Membrane potential means because of unequal distribution of ions across the membrane, and it constructs polarity. And how this membrane potential, that's simply, I told you already, the generation, that means the conduction of nerve impulse along the nerve fiber. Simply a momentary change in the membrane potential, that means the change in the ionic environment leads to the generation of action potential. How this environment change, what causes it change, and what are the basic issues associated with this, all we have to understand about for proper conduciveness of nerve impulse conduction. Okay, first these two are over, and how they maintain, that means how they maintain the negative inside and positive outside. There are three issues like leakage channels, voltage gated channels, then ligand gated channels. Leakage means sodium and potassium. Voltage are the same, sodium and potassium. Here more potassium leakage channels are there. In case of sodium, sodium gate, what we call voltage, it consists of two gates, one activation gate and two inactivation gate. Whereas potassium just contains only one gate, simply called activation gate. These are completely receptor chemicals, simply what we call, we'll discuss later. Okay, here these two are important at the moment. In this membrane, we found more number of potassium channels when compared to sodium. What is the consequence? It means membrane is highly permeable to, that means much greater permeability to potassium than the sodium. This is the point number one. and the voltage gated channel. There are two types of channels, sodium gated and potassium gated. Whereas for a sodium gate there are two, activation and inactivation gate. Whereas for potassium it is activation gate. Here, when there is a stimulus, say for example, a stimulus of any nature stimulates this environment, stimulates this ordinary resting environment, what we call, when there is no stimulus, what we call unstimulated nerve fiber, it is a exact environment, more negative inside, that means inside exoplasm, and ECF outside it is positive. When there is a stimulus, the ionic environment will change, that means there is a reversal. Here the positive will come inside and negative will go outside because of these issues, that means because of voltage gated channels. These gated channels, for example, voltage gated channels, they permit the influx of sodium from outside to inside, so that the inside become positive and outside become negative. And when this happens, it leads the generation of action potential, and this action potential conducts, that means travels along the nerve fiber. This is about basics. That means simply in the bottom line is clear. A momentary change in the membrane potential of a neuron through voltage gated channels is an action potential. Okay, and how we have to discuss in a sequence. Actually, there are 4 phases in action potential or nerve impulse conduction. What we call resting phase, next phase is depolarization phase, next phase is repolarization phase, then hyperpolarization, again resting phase. Okay, what exactly resting phase? I told you already. In the beginning, more negative inside and positive outside, and it has to be measured in terms of millivolts, called minus 70 millivolts. Resting phase is simply minus 70, more negative inside in the way of minus 70 millivolts. Here it is undisturbed. When there is a stimulus comes, and what happens? I told already, the voltage gated channels. See, the sodium voltage gated channels which are initially closed, that means the inactivation gate opens, whereas activation gate closed during resting phase. This is during resting phase. Whereas when there is a stimulus, these both, that means the activation gates open, activation gate of sodium open, and this, for example, here this is the nerve impulse, this is how the issuance, this is sodium gated channel, both gates they open, and this is potassium is still closed, and here there is different. The sodium gated channel, it is potassium gated channel. Here it is inactivation gate. This is activation gate, this is closed, activation, and this is potassium gated channel, that is closed. Okay, and here it is exoplasm, this is ECF, sodium ions influx, whereas the potassium ions it cannot because it closed. When the stimulus reaches the point, that what we call depolarization, that what we call the beginning of the action potential zone, the sodium gated channels open, that means the activation gate opens, leads to the influx of sodium inside the exoplasm from the ECF. When this happens, and it has, that means the stimulus should be what we call threshold stimulus. It should be minus 55 millivolts. That means initially the minus 70 millivolt resting phase has to changes to minus 55 millivolts, what we call a momentary change. This is called threshold. When this threshold touches, that means when we came into existence or minus 55 millivolts came into existence, then only we can generate the action potential. Then only it leads to conduction of nerve impulse. And minus 55 millivolts has been established. Later onwards, the influx of sodium means rapid influx, because the more number of channels are there, and rapid influx of sodium get inside the exoplasm, and it leads to a stage called depolarization, where the membrane potential changes to plus 45 millivolts. I told you already, a momentary change in the membrane potential. The resting phase minus 70, the threshold minus 55 millivolts, then to depolarization plus 45 millivolts. When this happens, the action potential generates, and it goes to the next successive part. But what exactly happens here? Simply it changes. I told you already, here the negative inside, the environment is same, here the negative inside and positive outside. Whereas in depolarization, it becomes positive inside and negative outside. This is very important. This is exoplasm and this is ECF. More positive because of rapid influx of sodium, because sodium activation gates, that means both gates got opened during depolarization. So leads to influx of sodium, that leads to plus 45 millivolts. That means the change in the environment. Then after this, the third phase will come, repolarization. There is one more gate we have discussed, the potassium gated channels. During this, the sodium gated channel, that means the activation gate remains open, but inactivation gate got closed. Whereas the potassium gated channel remains open during repolarization. The potassium gated channel remains open. Therefore, the potassium from exoplasm, ECF, got effluxed. They got outside. That means initially, during depolarization phase, there is more positive, plus 45 millivolts. But during repolarization phase, there is a change in the phase, because there is a change in the behavior of voltage gated channels. That means the sodium gated channel activation gate remains open, whereas inactivation gate got closed. Therefore, there is no influx of sodium from ECF. But here, since the potassium gated channel's activation gate opens, there is efflux outside. That means from exoplasm, the potassium ions go outside into the ECF. That leads to the change in the environment. Ultimately, the previous condition, negative inside, positive outside, it establishes minus 70 millivolts. This is very important. So then here the plus 45 millivolts become again minus 70 millivolts. What we call, again it is getting restoration of repolarization, simply polarization, what we call repolarization. Repolarization means restoration of the former status quo. The resting phase will come. Then the last phase, the hyperpolarization. What happens here? Both gates of sodium gated channels remains closed, whereas the potassium gated channel still opens. What happens? Still more number of potassiums, they go outside from exoplasm. That leads to the establishment of hyperpolarity, what we call minus 90 millivolts. Say more negative when compared to the ordinaries. That means minus 90 millivolts. Why this happens? Because potassium gated channels, which are called lazy channels, because the activation gate of potassium gated channel, they slowly close, and during this process much number of potassium ions, they go out, efflux, what we call, from the exoplasm to the ECF. Then minus 90 millivolts. So that means initially minus 70 millivolts resting phase, gradually when it touches the threshold stimulus of minus 55 millivolts, leads to depolarization. During this phase, both gates of sodium channels opens, and rapid influx of sodium from ECF to exoplasm leads to creation of depolarization, that means plus 45 millivolts. Then the repolarization phase, wherein the activation gates remain open but the inactivation gate closed, but potassium gate channel opens, that leads to efflux of potassium to outside, then that leads to creation of minus 75, then the hyperpolarization. Still, because potassium gate channels are lazy phases, they won't close properly, slowly. Okay, just like the inactivation gate of sodium as well. And when this happens, the minus 70 millivolt, because it reaches still more polarity. Still, when compared to the ordinary resting phase, it is at minus 70 millivolts. So then this is the entire scenario of a nerve impulse. The crux point is when the threshold stimulus touches minus 55 millivolts. What we call threshold stimulus, the action potential generates and it goes to the next environment. Then likewise in continue along the stretch of neuron. That means we have the basic structure of neuron. There are axon, the myelinated sheath, nodes of runway. Okay, this is about the basic scheme. For further consultation, I would like to take a small graph for better understanding how this happens and how the issues turn out. Say the form of the graph, is time. So this is minus 100 millivolts, this is minus 50 millivolts, this is 0, and this is plus 50 millivolts. Okay, during resting phase, say a resting phase is around minus 70 millivolts, minus 70. Okay, resting phase. When it touches threshold of minus 55 millivolts, it will generate action potential and it will reach down to plus 45 millivolts. That means depolarization. Then it will again come back, repolarization, minus 90 millivolts. Then hyperpolarization, minus 90 millivolts. Then again, when the potassium gate channel and activation gate got closed, again minus 70 millivolts got restored. So the first phase is resting phase. The second phase is depolarization. Depolarization. Now this is threshold. Then this is repolarization. And this is hyperpolarization. Again, it will restore. A simple schematic representation how different phases of a nerve impulse conduction. That means different phases of action potential come into existence. The thing is same. Just to change the ionic environment of a neuron for a while, for a momentary change, at least at the rate of minus 55 millivolt, it should be threshold. If it what if the stimulus won't reach minus 55 millivolts, there is no generation of action potential. There is no opening of activation gate of sodium ions. Simply the sodium gate, that means activation gate of sodium will shut down. There is no stimulation of, there is no generation and conduction of nerve impulse, what we call action potential. That means the nerve impulse, if it touches minus 55 millivolts of threshold level, then only it generates action potential. That leads to establishment of a principle called all or none principle. The crux point is minus 55 millivolts, which is a threshold. This is very important point. To conduct a nerve impulse, there should be a minimum, there should be a stimulus of minus 55 millivolts capacity. Then I have told you there are leakage channels. Apart from voltage gated channels, there are leakage channels. And there are more potassium leakage channels than sodium. I told you in resting condition, that means when the neuron is unstimulated, the condition inside membrane potential is with respect to inside the exoplasm. This is minus 70 millivolts. Leakage channel means that word implies leakage. The sodium, the potassium ions and sodium will gather, they leak inside and outside. That means the movement of ions from inside to outside happens. Whether it disturbs, of course it disturbs. Disturb this environment minus 70 millivolts. Then how it get regenerated when during a stimulus is option? That means what we call unstimulated conditions. Because of a pump, sodium potassium pump or ATPase. This will restore minus 90 millivolts. How? For example, this is the cell membrane, the neural membrane. This is exoplasm, and this is ECF. The more negative inside and more positive outside. It is minus 70 millivolts. And to restore this condition, this sodium potassium pump expels 3 sodium outside, whereas 2 potassium they come inside. 3 sodium it is removing from the exoplasm, whereas 2 potassium they getting entry into the exoplasm. The inference is more number of positive ions or positive charged ions has been removed from the exoplasm when compared to the negative. Since there is a dominance of negativity, what we call dominance of negative charges or membrane potential at the rate of minus 70 millivolts, that's how it is getting restored. Say simply in terms of molecular structure, I would like to tell you. Say there are 3 seeds. This is sodium, this is sodium, and this is sodium, and this one more one. This is potassium. Okay. Symport antiport mechanism. Simply just remember that this 3 sodium, then this is exoplasm, and this is ECF. It removes 3 sodiums to ECF, whereas 2 potassiums get inside. That means more positive getting removed from exoplasm. That is how they restore. That means sodium potassium pump maintains the membrane potential, that means resting membrane potentials. I told you the leakage channels, the voltage gated channels and others have an important role in maintaining this resting membrane potential. When there is a momentary disturbance in this, it leads to creation of action potential. For what they are creating? It plays a central point in cell to cell communication. And ultimately, how this happens. For example, say this is a neuron. Okay, and this myelinated sheath. This sodium potassium voltage gated channels, they concentrate in the nodes of Ranvier, what we call nodes of Ranvier, and this is myelin sheath. Here the first point, action potential generated, then it leads to jump into the next phase because there is a myelin sheath here. It is here the conduction is not continuous. It is called saltatory jump. It jumps from one point to another. Saltatory, what we call simply saltatory conduction. And its speed depends on the diameter of axon. Is very important point. Why saltatory conduction? In evolution, saltatory conduction plays an important role when compared to the continuous conduction, because continuous conduction should travel along the nerve fiber. It may waste stuff. It may take much time. During this process, adverse consequences may come. To avoid this delay, evolution of saltatory conduction has been emerged. Just like kangaroo jumps from one node of Ranvier to other, and its speed depends on, that means the conduction speed depends on the diameter of axon. The higher the diameter, the higher the speed. Okay. Apart from this, I think we are clear. So it's about action that means nerve impulse conduction. The ultimate objective of this nerve impulse conduction is to generate neurotransmitters. I told you already, neurotransmitter. The word it implied. It transmits, that means the action potential or nerve impulse should transmit from one neuron to another neuron. This is neuron 1, for example, and this is 2, and this is called synapse. These are called synaptic vesicles. And they are called ligand receptors, and they are channels. These are ligand receptors. These are synaptic vesicles. and they are neurotransmitters. This is postsynaptic. This is presynaptic. This is synaptic cleft, what we call gap. From presynaptic, synaptic cleft, and postsynaptic become synapse. You know, the neurotransmitters come here and they will bind here the ligands, ligand gated channels, what we call ligands, so receptors, and they will go inside and they will again start action potential. You know, neurotransmitters are of two types, either excitatory or inhibitory. Inhibitors say glycine, GABA means gamma aminobutyric acid. Here acetylcholine is most common neurotransmitter, acetylcholine. Apart from there are other excitatory and inhibitory that both may act, for example, dopamine, serotonin, etc. You know, epinephrine, for example, another example, norepinephrine. Different neurotransmitters. Depending on the kind of neurotransmitter, the potential may be excitatory post inhibitory potential, excitatory or inhibitory. Excitatory postsynaptic potential or inhibitory postsynaptic potential. Simply called excitatory postsynaptic potential, inhibitory postsynaptic potential, depending on the kind of neurons. For example, inhibitory neurons, say neurotransmitter, say glycine, it leads to inhibitory postsynaptic potential. You know, excitatory and inhibitory postsynaptic potential depends on the kind of action. I told you already, the ultimate objective is to generate neurotransmitters, and the kind of neurotransmitter, the response will come either inhibitory postsynaptic potential or the excitatory postsynaptic potential. Simply, it is called synaptic transmission. Synapse means the thing about the junction between the two neurons. The synapse. It is a structural gap, but there is a functional bridge. Because it is nothing but, you know, what exactly happened when the action potential reaches this axon terminal. You know, this axon terminal, the synaptic vesicles which contain neurotransmitter, they will fuse. How? There will be calcium voltage gated channels. That means change in the membrane potential so that the calcium voltage channels, and these calcium makes the movement of synaptic vesicles so as to fuse with the presynaptic membrane, and through exocytosis they release the neurotransmitters in the synapse, and they will bind with the ligand channels and they will cause either excitatory or inhibitory synaptic potential, synaptic transmission. This is how the issue ends. And what another important thing is a refractory period, what we call refractory period. Is there any possibility for the generation of second action potential when the first action potential is in process? Generally may not. It is called absolute refractory period. And to conduct a second action potential, the first action potential, that means the stimulus of the second action potential should be stronger than the first one. Then the second action potential may be generated. That means what we call a relative refractory period. So it's about the nerve impulse conduction. I hope you enjoy all these, my classes well. I told you already, you have to follow a basic reference and a basic standard book, and you can consolidate your knowledge based on my YouTube channel, especially for the poor and talented students. Okay, thanks for watching.